Good afternoon, everyone. Welcome to this seminar. So today we have Dr. Arka Chatterjee from UPES Dehradun. So he works in the area of X-ray imaging of accreting black holes, general relativistic effects, and disk jet connections in these systems. So he has discovered jet-induced soft lag during accretion onto black holes, and expertise in ray tracing, black hole astrophysics, and time series analysis techniques. So he has been also member of International Astronomical Union, Canadian Astronomical Society, and ASI. So most welcome. Yeah, you can go ahead.
I think I'm audible. And this is my second time standing here in this podium. The first time we simulated the images of black hole was presented in Redco 2. That was back in 2015. So from there, we have emerged a little bit, and we are going to talk about the basics, very fundamental pillars of X-ray images of black holes. And to begin, first thing is that, of course, there needs to be some introduction. And this image represents the quest of life, a quest of knowledge. And you can see here, one particular person is poking behind the curtains. And this is what astronomers do. They poke and extend the observable universe. So this image, in my idea, could represent astronomy as a whole. Now, to begin with modern astronomy, we can start with Galileo Galilei back in 1609 when he developed the optical telescope, and from there we went to VLT. It's a 400 years journey. So in this 400 years journey, lots of things changed. Of course, one thing is that bigger is always better. So apart from that, there are several other techniques which are changed. Now, along with optical, there's ground-based radio and submillimeter astronomy, which emerged a lot. And there are optical counterparts, the counterparts in India, in ARIES, there are lots of telescopes and lots of radio telescopes that you can find in Indian context as well. But X-ray astronomy is a little bit challenging. It's challenging because you have to go to space. And our atmosphere is very thick if you are considering X-ray. Thankful to that, we are surviving. And the first X-ray telescope, apart from the probes or balloons that we can mention, the first X-ray telescope is Uhuru, which, yeah. So this is the first light curve that was gathered by Uhuru telescope. And then from there on, you have a fleet of X-ray telescopes that are that have been operated or being operational right now. So the paper was published in 2021. Since then, you can see some of the red satellites are already working and they are operational, such as IXP and GRISM. Fantastic data. And hopefully in later years, more will come and the fleet will be expanded. Now, when we were talking about X-rays, and we need to talk about the accretion physics as well. So in case of accretion physics, a few things we have to remember. So first thing is that who can accrete? Stars can accrete, white dwarfs can accrete, neutron stars, black holes, they all can accrete. And black holes are accreting over a very large mass scale, starting from 10 to 10 to the power 9. So it's an order of 8 to 9 solar masses when we are talking about accretion physics. So how do they accrete? They accrete from their binary companion, they accrete from interstellar medium, they can accrete through tidal disruption event. So completely destroying the star or partially destroying the star. So the modes of accretion: Roslow overflow, outflows from companion, and TDEs, as discussed. So a very basic instance of black hole is a region of space and time where the escape velocity is more than the speed of light. And it was conjectured from Newtonian physics by John Michell in 1783. So if you have a very compact region where escape velocity is very high, then you have a very dense dark star. That was later got the name of black hole. Now, if you calculate the mass that a black hole requires is at least 3 solar mass. Below 3 solar mass, you can get neutron stars. If you go beyond Chandrasekhar's limit, you will get white dwarf. But after 3 solar mass, what you get is a black hole. So gravity wins everything. Neutron degeneracy pressure, electron degeneracy pressure, you have overcome everything, you got a black hole. Now, how do you get the name of black hole? The name of black hole has a tragic history. The word originated from Kolkata, previously known as Calcutta. There, 146 British inhabitants were killed. And not 146, but 146 inhabitants were imprisoned in a very small cell. Only 23 came out alive. And British press designated that cell as Black Hole of Kolkata. Now, this word black hole is a loose translation of Andhokup, Andha Kua. So the translation got from Bengali to English and then again retranslated in Krishna Govar Tham Bengali say, which is not apt. So in any way, later DK proposed that this black hole word could be used for collapsing stars or dark stars. So that's how black hole is connected with India. Now, black holes are detected via several processes. You can detect a black hole using microlensing process, Doppler effect, astrometry, accretion, gravitational waves. Currently, the population of black holes are being detected with gravitational waves are getting larger and larger with each days. And the population that are being discovered by accretion are also getting larger and larger, with more fleets working into this particular domain, with more multi-wavelength campaigns. You can precisely determine their mass, their distance, and other aspects. So accretion is one of the best techniques to get the black holes information, discover black holes. So in that particular context, galactic black holes are extremely valuable. The valuable part lies in their life cycle. If you see an outbursting black hole like this, these outbursts are some sort of transient phenomena which occurs and lasts for 50 to 100 to 200 days. So it's a phenomena where a black hole and the accretion process around it evolves. So black hole evolves because it's devouring some mass, and angular momentum. So it will gain some angular momentum and mass during this process, and it will leave the imprints of its habitat by giving these photons. So these X-ray photons, they are coming from very nearby regions of a black hole. Now, this particular black hole went into several outbursts. So we will try to understand how these black holes are generating these photons. The very basic idea of generating photons comes from this particular equation. You have one particular object which is flowing inward to the gravitational well of a black hole, and it is losing potential. Now, if you want to conserve the energy, that potential must be transferred into kinetic energy. Now, if you have enough kinetic energy in that system, of course, whatever kinetic energy you can have, you can apply that equipartition theorem and get the temperature. And if you can create such a velocity profile where temperature reaches up to 10 to the power 7, 10 to the power 6 Kelvin, you can get some radiation, optical, UV, then soft X-ray radiation. So that's the entire mechanism of accretion to radiation. Now, this radiation, accretion to radiation is not that simple. We need to dig deep and see how these H news are generated. So to understand a few parameters, let's look into the numbers around black hole accretion. The electron temperature is roughly 10 to the power 7 to 10 to the power 9 Kelvin. And the velocity of one electron moving around the ISCO, which is innermost stable circular orbit, is 0.5 c. Now, if you compare this, the Bohr, first orbit of Bohr electron has 1 by 137 c. So you can see the electron is moving nearly ultra-relativistic speed. And the frequency corresponding to 10 solar mass is roughly of the order of 218 Hz. Fluid is completely ionized because your electrons are and protons, they are separated because it's so high energy. So electrons will freely interact with photons. Now we'll dig deep more how this is happening. So first thing is that the effective potential. So if you look into this particular potential, the first two terms corresponding to the central field potential of any Newtonian object. The third term, which is the L square by R cube, it is the speciality of black hole. It's not a speciality of black hole, but if you go beyond a certain radius R, speciality of not say GR, it will applicable to all of the masses. But if R is such small, then only this term starts to dominate. And that small r can only be achieved through a black hole. So the same potential will be applicable to a star because it's derived from Schwarzschild solution. And Schwarzschild solution is not restricted to a black hole. It's a spherical mass. So you can have a mass of star, neutron star, anything. But you need to go beyond a certain radius r, below a certain radius r, to have this third term dominating. And that is only possible for a black hole. Then what will happen? Everything will start to fall. There is no escape. So matter will start to fall. So there you get the first sight. So as you go close and close to a black hole, your frequency increases. You are radiating more and more energy, just because your drop of potential is higher and higher. So you can say the first painter of the X-ray image is the potential. Now it differs from planetary bodies, neutron stars, and white dwarfs. Now it's much more than what it meets to the eye. You can see these are rings, beautiful rings around Saturn. what does it mean? So if you have a potential like this, and around that potential, you have particles which are orbiting. It starts to orbit. There are several kinds of orbit which you can find. The minima will correspond to a circle. The eclipsing part corresponds to the 2 points of intersection. If you are bouncing with the angular momentum, then you will get this kind of orbit. And if you have enough energy to overcome this angular momentum, then you will plunge into a black hole. So these are particle orbits. They will never form a stable anything to sustain for 200, 300 days of radiation. Just we have discussed earlier. So there are 200, 250, 300 days of radiation. You need something sustainable. And there comes viscosity. So you have fluid, that fluid has viscosity. Viscosity means it creates differential rotation. It creates a situation where Vr is much less than V phi. So the matter is rotating around the circle, but it's not infalling directly. So you have viscosity. If you go back to your BSc first year's class, you will find that this effective potential, it looks like a central field. So in central field, you don't get heat, right? Where would you get heat? So you need to introduce viscosity to generate heat. You need to introduce viscosity to make the potential non-conservative. And then that non-conservative potential will heat up the fluid. The matter starts to lose angular momentum. Then it goes inward. It generates torque. Now your disk is not bound to the Keplerian plane. You can move. See, once you have Keplerian angular momentum, you are bound to a Keplerian plane. Once you introduced a non-conservative force, it's not bound anymore. It can go up and down, do here and there, whatever it can do. So you are not bound. So it creates viscosity. Viscosity will create a disk, optically thick disk, multicolor black body, so on and so forth. So, oh, sorry. So this particular disk will be there for our radiation purposes. So again, you can see in X-ray regime, you can get this kind of disk. So this is our second painter, viscosity, which creates the accretion disk. Now, if you look into spectra of any galactic black hole, outbursting galactic black hole, X-ray spectra, you will find that there are two parts. One is a disk black body part, the other is a power law. And that power law is supposed to be generated via inverse Compton scattering. Now, this inverse Compton scattering requires high energy electrons. Now, this high energy electron is surrounding the Keplerian disk and then a very close region to a black hole. And this is the corona structure. It's highly debated. People will start shouting this corona, it doesn't mean anything, so on and so forth. But the essence is you have high energy electrons, and these high energy electrons will produce this power law. So if you look into this particular graph here in the right hand side, you can see the black one corresponds to the lowest electron energy. And as you increase the electron's energy, the power law is increasing. So more and more inverse Comptonization occurs with the electron temperature. And these can be observed for Cygnus X1, where spectral hardening is observed, and various other sources. And some of you have already calculated fitted data for galactic black holes and AGNs where you have calculated KTE. It is supposed to be a very important parameter for galactic black holes as well as AGNs. So you have your third painter, which is the electron temperature. Spectra will harden with increasing electron temperature. Now, just what I said earlier, that your Compton cloud shape or corona or whatever it is, it's highly debated. But the takeaway message is there's no debate that high viscous matter should be in equatorial plane, and low viscous matter could be off equatorial plane. So because of the stability, okay, Keplerian plane will provide most stability. So high density, high viscous matter, we would like to stay there, and low viscous matter will spill out. So there's no debate about that. Now, what happens to the other parts of observation? So if you change the inclination, now as you change the inclination, what is inclination? Suppose we have a plate and you are looking from top, that is zero inclination. And if you are looking at this edge on, your inclination is 90 degrees. So if you increase the inclination, you can see that in this particular image, low inclination systems have a less spread of disk temperature, and high inclination systems have a higher spread of disk temperature. This is the accretion disk temperature, black body temperature. So harder spectra is expected at higher inclination. This is observational fact, not a theoretical argument. So whatever be your theories, you have to modify it according to the observation. So there comes emitter observer frame transformation. That means your observer and your emitter is connected to or connected through one and only possible way, that is the photon propagation. And photon propagation is little bit tricky around black holes. Photons bend. So if you incorporate the bending, you will see that at high inclination angle, your disk is wrapped. It bends upward. So we incorporated that particular aspect and made some images and studied what kind of effect these bending could incorporate or to make during the accretion process. So there could be spectral variation, there could be temporal variation. So we have incorporated these relativistic correction, and for nearly zero inclination, 0.01, you cannot do numerical simulations with zero actually, because it will create some bizarre results. So we did some 0.01 inclination, and you can see the spread. This is the color bar which corresponds to the Doppler effect. So any line will be split. So you can see that there is no splitting, and the same accretion disk would be split into several colors if you go at higher inclination, let's say 80 degrees. And this will essentially be reflected in the temperature profile. So if you take one particular line, let's say 5 kV, 3 kV, 2 kV, whatever be your line is, those lines will be split into a several area. And this particular diagram, the vase shape, represents the temperature profile according to the redshift. So if you see, this redshift will determine how and what amount of deviation for a particular line will create. So these are the effects that you can create for different inclination. The same thing with nearly zero inclination, the line will not split, it will be an individual line. Again, if you choose different kinds of geometry instead of a disk, if you choose a torus, your splitting will be different, stuff like that. So what it does, the emitter observer frame transformation or bending effect, is that if you look into this particular part, this is the black body spectrum of that particular disk, same as 10 degree and here 80 degree. The difference, you can see that the black body top is flattened. 10 degree a little sharper, 80 degree is a little flatter. So by comparing these two, you can see that the disk temperature is flattened. Just what you have seen observationally, the spread of disk temperature for high inclination objects are much more compared to the low inclination objects. So what it does to the timing properties, if you look into the timing properties, you will see that the QPOs which are observed for high inclination sources have a little bit higher fractional RMS, and low inclination QPOs RMS is a little bit lower. On the other hand, the time lags on the QPOs shows negative lag for high inclination sources and rarely shows negative lag in low inclination sources. So these are two aspects that can be assessed from the emitter observer frame transformation. So our fourth painter is inclination and bending of photons. So what it does, it hardens the spectra. QPO power increases with high inclination, and soft lags are observed at high inclinations. What about spin? So, and what about the other aspects, right? Reflections and stuff. So if you introduce spin in the system, what happens is that geometry changes, your photon orbit change, particle orbit change, and a scenario drastically changes if you go beyond 6 Rg, within 6 Rg. If you are away 6 Rg, apart from further from 6 Rg, you are still okay, but if you are inside 6 Rg, dramatically things change. What it changes is, like, if you have a prograde orbit, meaning your black hole is spinning in this direction and your accretion disk has also the same direction of spinning, then your prograde orbit will have closer interaction with the black hole. And if you have a retrograde orbit, which means black hole is rotating in this direction and the opposite direction is the rotation of the accretion disk or the material. So you are further away from the accretion disk. Observationally, these are seen from the iron line. Iron line is one particular line which is observed in 6.4 keV and very widely celebrated in X-ray astronomy. The reason is very simple. Iron is the most stable element, and iron K alpha is within the 10 keV range, 1 to 10 keV range. So that particular line is good to study for general relativistic aspect, good to study thermal aspects, and a lot of aspects which will be done in 0 to 10 keV regime. So most stable within that range. That's why iron is so important. So these spectral line features and reflection hump are visible, and they are calibrated through various models. Not the models are actually reliable theoretically, or their fundamental properties are robust, but they are some sort of tools to understand the geometry and the spectral properties. So how you know observationally that your system is a prograde system? You look into the residue pattern. So if you look into this particular residue pattern, and here as well, you can find one-to-one correspondence. So theoretical prediction is this particular distortion, and you can some sort of similar pattern can see from this X-ray spectrum. So this is a comparative study that you can perform whether you are encountering a prograde system or a retrograde system. If it's a retrograde system, so the 3 to 78 spectral residue, this particular spectral residue will almost similar to this spectral residue. No, it's not ACD, it's the residue of that. So let's go back. Oh. Yeah, so this one particular spectrum which is fitted with a power law. Now, if you fit a spectrum with a power law, that means it's a straight line. Now, on top of that power law, you get some residue. That residue is plotted here in the lower panel, that ratio. Now, that residue, if you compare that residue with the hump, so that the image below, this is again, this is the hump and the distortion corresponding to the prograde and retrograde orbit. This is an ACD. I will not say ACD. I will not say ACD because ACDs are usually go for broadband. This is a very narrow band energy distribution, you can say. Y-axis, yeah. Okay. Yeah, continuum emission. Yeah. This ACD is without Comptonization. So that's why I'm saying that I would not go for this by ACD. This is only ACD for iron with reflection and gravitational broadening. There is no Comptonization. So only, yeah. 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 So if you put Comptonization on top, then it will be ACD. So right now, this comparison suits with the ratio. Yeah. Mm. 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 Yeah, yeah, and reflection. Yeah, and reflection. It will be a little bit shrink. Mm. Yeah, yeah, yeah. That's why. Let me rephrase. Let me rephrase. When I talked about these models, I specifically said they are not robust with theoretical arguments. So yeah, so they are not robust. Yeah, yeah. So they are not robust. Even when these models, if you look into these pictures, you can see there's a stupid dot here. It's supposed to be a lamppost, and this lamppost is considering it can have iron, and this iron can be reflected and stuff like that. So there are lots of models, and these models will predict different kinds of line structure depending on the position with the black hole. So considering this, you have the residue, and these residue can be mapped with the emission profile. So essentially, if you look into this particular emission profile, it will have a spectral counterpart, as well as a temporal counterpart. So the direct emission will reach you a little bit faster, and reflected emission lines will reach you a little bit later. And that's some. Hmm. Yes. Hmm. Yes. Yes, that is also possible. With the variation of impact parameter, you can have a lot of timing features which are changing. But now the question is, not all impact parameters will reach to a certain observer. So there is a parameter space of impact parameter which is very narrow for a particular observer standing at a particular inclination angle. So that will reduce the number of photons that can contribute to the timing aspect broadly. There is, of course, there will be some contribution, but the contribution to have significant effect, it will take the number of photons to be higher side. So in any case, black hole reflection and of course this bending effect will be much more important, and the photon travel time will be much more if you are considering extreme car scenario, where particles can rotate several times in different planes and then finally reach to an observer. Yeah, yeah, yeah. So if we consider this sort of geometry, then this type of geometry, lamppost, then you will not be able to find that kind of relationship. Okay. Okay, so if you go to higher inclination, so let me go back a little bit again. Let's look at this particular spectrum. This is the Comptonized spectrum, high energy spectrum. Now, if you are in high inclination, your photon, suppose this is your disk and this is your cloud, this region, and you have a disk surrounding it. Your observer is sitting somewhere here, high inclination. So these soft photons will be bent like this, and these bent trajectories will enter into the Compton cloud or corona, starts to interact and come to your observer who is sitting at a high inclination. So the effect of high hard energy photons will increase if an observer is sitting at high inclination. The ones that are actually entering the Compton cloud will be less. So we can see, so the number of hard photons are less. Yeah, Comptonize. And so again, so what we have currently is that we have reflection and stuff like that. So our fifth painter is spin and reflection. So essentially, if you need to paint an image of a black hole, you need potential, viscosity, electron temperature, spin, reflection, and bending with inclination. So if you put all of them together without the spin, you get this kind of image. So this is the first X-ray image, simulated synthetic image of a black hole. So we did. So no, this is actually the first X-ray image. So before that there were no X-ray images where you have spectral and temporal counterpart. Synthetic images, of course. No, that was purely disk. optical, you can say, but yeah. So earlier also, mostly though the images, the two components, one is the comptonization and the other one is the disk. With this setup and with spectral and temporal counterpart was not done. So in any case, you can play around with various parameters and make catalogs, and you can play around with hydrodynamics and with outflows, and you can create spectrum, synthetic spectra, and you can create synthetic images where you have outflows, and then you can see the evolution of outflows. So essentially, if we look back here again, you can see when you are seeing an accreting black hole, the central region, the photon sphere, consists of high energy photons only, not low energy photons, because your low energy photons are already exhausted while scattering in the Compton cloud. So if you want to get highest amount of redshift, that highest amount of redshift could be coming from more than 10 keV photons. So that one particular aspect that we did, and these are nearly 2 billion photon simulation. So otherwise you will not be able to generate images. One particular image like this, it requires 1.1 TB of data, just to give you a perspective. Again, let's go back. So spectral hardening is occurring due to photon bending, and then you can map each photons with the time of arrival map. Just what Professor Chattopadhyay was telling, that you can map the photons, each photons, on an accretion disk. And since our code, our method is completely unitless, these are translatable to AGNs as well. So you can get inclination effect. You will see that with higher inclination, the lag is getting lower and lower. For some reasons, it will change to soft lag when the jets are dominating. That is a complete separate aspect. So what is the uniqueness of our approach? We have full GR forward ray tracing in-house, thick disks, electron cloud, hydrodynamics, and etc. So the big question is, yes, so that radiation corresponds to synchrotron. So the image that you see for EHT, they are most, at least for M87 that I can say, that is near face-on view. So you are observing through the jet. Yeah, so observing through the jet. So while observing through the jet, it is expected that we would be able to see the photon ring. It's not actually the photon ring. So it's the near about region which is having the highest brightness feature. So you can no, that is not true actually, because high energy photons will be there, but since M87 and Sagittarius A both are low luminosity AGN, because their accretion rate is very less. So in that case, low luminosity AGNs tend to have more effect of magnetic field than the accretion. So mass accretion rate has some effect, but the effect of magnetic field surpasses that. So you have synchrotron radiation dominating the Compton radiation. So if you look at the broadband spectra, are those EFE? Because if you multiply with energy, then the Compton hump will be there. Otherwise, yeah, if otherwise, could be. No, that is true. Keplerian part will not be there. Keplerian disk, if we look into the luminosity versus, yeah, oh yeah, sure. So how do we capture X-ray images of black holes? The simple answer is X-ray interferometric process. So you need X-ray interferometric missions for that, and for AGNs, let's say you have 1 megaparsec distance, it requires 1 microarc second. For galactic black hole, let's say you have a galactic black hole at 10 kpc distance, it requires 10 to the power minus 6 microarc second. So you need X-ray interferometric missions for that. The science cases with X-ray interferometric missions are extremely rich. You have supermassive black hole accretion, then AGN feedback, black hole winds and feedback. There's a number of lists that you can add on, and this list is increasing day by day. So of course we have added one more candidate, one more aspect in this particular list. Probably I don't have time for that today, but later on we can discuss. So the challenges are it is either lunar or space-based mission. Very high stability is required for this X-ray interferometric missions. Fleet costs are high. Your effective area calculation needs to be very precise because when you are building interferometry and you are in the X-ray regime, let's say you have very small energy band, even that small energy band can smudge the image, because as we all know, the interferometry requires one fixed frequency. So you need effective area for different energy bands so that you can allocate various area for various bands. And currently there's no Indian mission concept. There are two concepts. One is by, not one, actually three concepts. One is made by ESA's 2050 vision by Phil Utley, and then thereafter you have Oshad Gandhi, who proposed a lunar mission for this particular X-ray interferometry. And the current and the most promising one, which is currently going on with NASA's 2050's vision, is these fleet of satellites which will be collecting and performing X-ray interferometry. So of course we can write several proposals for at least white paper combining all aspects of interferometric missions, like the ones that we discussed earlier, and there could be many more which we can add, and that white paper could serve us for later years while proposing for such kind of missions. But yeah, X-ray interferometric mission will be there because ESA has a counterpart. ESA and NASA both have their missions. JAXA is recently preparing one. So it should be us who will do the next this white paper thing. So let's hope we all can collaborate and establish something. I guess. So this particular telescope works as the hub where data is collected and the interferometry is done. The other fleets, which are smaller, they are used for collecting several. Yeah, it's a fleet. It's a fleet. So LISA has 3 telescopes which are operating in space, not operating, will be operating in space for specific configuration, somewhat similar, but the number of satellites will be much higher. Now, there are several alternate processes for this, because some might say that you have no, not fixed. With fixed configuration, it will be a little bit harder to get the actual stability. Without fixing the configuration, it will be a little bit easier. So these are all written in this particular Weaver's 2026. There are at least 2-3 Indian participation there, one of whom has worked in SN Bose, Ruchi Pandey. So she's in optical. No. Ruchi here. Yeah. So Ruchi was here, and then yeah. So currently we have a communication with Weaver, Kimberly Weaver. So right now, let's see what happens. So anyway, so I guess that's it. I have some more slides, but later first. Yeah, people are bored, and so punchline is probably this. So see, these are my conclusions. So you have some painters of black hole images, then you have science cases for X-ray interferometry, and this part might be later. So thank you. Maybe I'll come later, and again, then I can do that. Yeah. Yes. Yeah, those are, yeah, dormant black holes are a little bit difficult. If you are trying, yeah. You want to detect electromagnetic counterparts, so either accreting or maybe even in quiescent state you can try, but you need some radiation. Detection. Yeah, there are plenty of, like yeah. Nasty weight. Yeah. 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 Go ahead. So features, first thing is that you have, if you want to do Monte Carlo simulation to generate images, it doesn't look pretty. So that's what I can say in the first image. So reviewer was very skeptic because it's not pretty. So that's one thing. The outside is very smooth because it has a very distinct temperature profile. So the radiation is well defined. But when you go inside this cloud, if your cloud has temperature gradient, it will look different. If you have single temperature corona, then it will be very smooth. If you look into this part, it's little bit more bright than this region. Little bit less bright because of the Doppler effect and the rotation. Okay, so, and this inside region, this is the photon ring, which is entirely made up of high energy photons. This stochasticity resembles that various photons can emerge from various depths of corona as they will have different optical depths at different coronal layer. So all the photons that you see here are last scattering points, and these are not surface scattering only. Photons can scatter within the corona and leak out to the observer. So that's about it. And if you have further question, you can ask. Yes, only. 4D. 4. Yeah, yeah. You can find lines in neutron stars as well. You can find not that much spread out lines, but some sort of spread out lines from neutron stars as well. So it's highly possible to get these lines. But whether that model is applicable to neutron star, so I can't figure out which one? This one. This one. There is no. No. It's not by chance. You take any AGN. Suppose there is MCG -6, Tanaka's paper, famous nature paper. So you see they have done the same thing. So what they have done, they have fitted the entire spectrum with a power law, which is basically a straight line. You take a straight line and see whatever is going up and down. So this is the power law fitted, and then whatever up and down is the residue. And that residue looked like this. Yeah. Yeah. Yes. Yeah, that's why I said there is a challenge regarding the effective area. So effective area in any case means that you need more photon, gather more photon to get more better image. Okay. So those who do optical astronomy, they know that effective area or area, how much importance it does have. I guess it's more important than the focusing factor, somewhere like that. So effective area determines how many photons you will catch, and that's something you need to optimize. How many satellites you can send, what is the optimum level the effective area would be, and that effective area needs to be corrected for each energy bands in a given range. So stuff like that. Yeah. So actually I didn't say anything. That was Weaver. So they said. Yeah. So you have one black hole moving in this particular direction. It has a spin like this. Now your accreting matter is rotating around this. Okay. So this separation of angular momentum will create retrograde orbit. If you have both of them moving in the same direction, black hole is moving in this direction, your matter is also, accretion disk matter is also moving in the same direction, it will be a prograde orbit. So you can encounter that only when you have Roche-Lobe overflow from a wrong direction, mostly from winds. So if you consider Roche-Lobe overflow through L1 point, then it is most likely to become a prograde orbit. If it's wind fed, it's coming from all over the space. You can get retrograde orbit, prograde orbit, whatever. Nobody knows. So that could happen. But prograde orbits are much more likely, because from L1 point, you get most of the accreting outbursts or persistent sources. So mostly they are from L1 point. Few, like Cygnus X1, is wind-fed. But that is also a small accretion disk. It creates lots of trouble for people. Okay. Thank you for listening.